At Cloud Next in April, Google announced the 8th generation of its Tensor Processing Units, and instead of one chip, they shipped two, TPU-8T and TPU-8i. Same generation, same silicon family, completely different jobs, and once you understand why they split it, you'll start to see where the entire AI industry is actually heading. Not toward one giant do-everything chip, towards specialization. So let's get into it. Quick reset so we're all on the same page. Your laptop runs on a CPU, a small number of extremely smart cores that can do basically anything, but only so many things at once. Great for general computing, terrible for AI, because training a model is not complicated work, it's simple work repeated trillions of times. Matrix multiplication over and over at a scale a handful of CPU cores just cannot touch. GPUs stepped in almost by accident. They were built for rendering video game graphics, which mean thousands of small cores doing simple math on millions of pixels at once. Around 2012, researchers realized that neural network math and graphics math are basically cousins. Both are huge grids of numbers getting multiplied and added in parallel. That coincidence is the entire reason Nvidia is worth what it is today. But here is the thing people forget. A GPU is still a generalist. It does graphics, physics, simulations, crypto mining, and AI, and it's decent at all of it, but not built specifically for any of it. Google looked at that and then decided decent was not good enough. Now, Google has been building TPUs since 2015, not general-purpose chips, chips with exactly one job: matrix multiplication, done as efficiently as physically possible. The core trick is something called a systolic array, basically a grid of tiny processing units where data flows through the chip like water through a pipe instead of getting fetched from memory over and over again. Less waiting, less wasted power, more actual math getting done per watt. For years, this ran quietly in the background. Search ranking, YouTube recommendations, translate every version of Gemini. You've been using TPUs constantly without ever knowing it. And in Google's own words, this 8th generation is the culmination of more than a decade of development, and honestly, that tracks with the whole Google hardware philosophy: building the thing, running it internally for 10 years, and then letting the rest of the world catch up. Now here's the insight that took the whole industry a while to really absorb. Training a model and running a model are not the same task wearing different clothes. They pull hardware in opposite directions. Training is a compute bound. You're shoving massive batches through the network again and again, and what you need is raw throughput plus insane bandwidth between chips so thousands of them can share information every single step. Inference is a different animal entirely. It's memory bound, the model is not crunching one giant batch, and it's generating token at a time, waiting on memory in between. And now, layer AI agents on top of that. An agent is not one query, it's a loop, calling tools, reading results, planning the next move over and over. Google actually called this out directly, saying models now need to reason through problems, execute multi-step workflows, and learn from their own actions in a continuous loop, which all places a completely new set of demands on infrastructure. Once you accept that training and agentic serving are pulling in opposite directions, splitting the chip stops being a gimmick and starts being the obvious move. TPU-8T is built for scale, plain and simple. A single superpod links 9,600 chips together, sharing 2 petabytes of memory with double the interchip bandwidth of the previous generation. And Google says that the whole thing delivers 121 exaflops of compute, close to 3 times the performance per pod of Ironwood, last year's chip. With the new Virgo networking fabric, plus something called TPUDirect, which pulls data straight into the chip and skips the usual bottlenecks, Google claims near linear scaling up to 1 million chips in a single logical cluster. What I actually find more interesting than the raw numbers is the reliability engineering underneath it. Google is targeting over 97% goodput, meaning that the cluster spends almost all of its time actually training instead of stalling out. They are doing that with real-time telemetry across tens of thousands of chips, automatic rerouting around bad network links without killing the job, and optical circuit switching that reconfigures hardware around failures with zero human intervention. At that scale, every percentage point of downtime is potentially days of lost training time, so this stuff matters just as much as the flops. Now, the inference chip, which is where things get more interesting. Google is calling it the reasoning engine, and the whole design is built around killing what they describe as the waiting room effect. Basically, the idle time chip spends inquiring requests instead of actually responding. TPU8i pairs 288 gigabytes of high bandwidth memory with 384 megabytes of on-chip SRAM, triple the previous generation, which keeps a model's active working memory sitting right next to the compute cores instead of a longer trip away. It also runs on Google's own Axion ARM-based CPU with double the physical host per serving and an NUMA memory setup for better isolation. For a mixture of experts models, specifically interconnect bandwidth got doubled to 19.2 terabits per second, riding on a new topology Google calls Boardfly, which builds up from small 4-chip clusters into groups of 8 boards and stacks 36 of those groups into a full pod. There is also a new collectives acceleration engine on the chip itself that reportedly cuts certain latency bottlenecks by up to 5 times. Put together, Google is claiming 80% better performance per dollar than Ironwood, which they say translates into serving nearly double the customer volume at the same cost. And there is a genuinely clever detail buried in their own write-up, because they say that the SRAM capacity was specifically sized around the memory footprint for a reasoning model's key value cache at production scale. That is not a generic spec bump. This is a chip built around actual shape of how modern reasoning models eat memory. Both chips, by the way, run on Google's Axion CPU host for the first time ever, top to bottom, and both claim roughly double the performance per watt of last year's generation. Google also says that its data centers now deliver 6 times more compute per unit of electricity than they did 5 years ago, and this generation is built to continue that curve, backed by a 4th generation liquid cooling system. Just like the American dream promises each generation a better life than the one before it, every new TPU generation promises the same thing in its silicon: twice the performance per watt, less weighting, more room to grow, and proof that progress isn't just a human tradition anymore. Nvidia's entire strategy for the past decade has been one chip that does everything: training, inference, scientific computing, all on the same GPU family, and it worked incredibly well for them, but they still control the overwhelming majority of the AI accelerator market. This is not a David versus Goliath moment yet, but Google is making a structural bet that the generalist approach has a ceiling. As agentic workloads keep multiplying and inference eats a bigger and bigger share of total AI compute industry-wide, a chip actually engineered around waiting less and moving cache data faster is not a nice to have anymore. It's the difference between an agent that feels instant and the one that feels, well, sluggish. Real customers are already validating it too. Citadel Securities have publicly said that they are running cutting-edge workloads on TPUs, and Google has previously disclosed independent inference cost comparisons showing meaningful savings over comparable Nvidia setups. I think this split chip approach is going to age really well. Not because Nvidia is in trouble, because they're not, but because it signals where serious infrastructure players are heading. You either specialize your silicon around the actual shape of the workload, or you leave efficiency on the table forever. Google clearly decided the extra engineering complexity of maintaining 2 chip lines was worth for the efficiency at planet scale. So, no, Google is not replacing GPUs overnight. Nvidia stock barely blinked on the announcement day, but architecturally this is a real signal. Training and inference have diverged enough that a single chip trying to do both well is starting to feel like a compromise nobody actually wants anymore. And when the company that has been quietly running its own AI infrastructure for a decade decides to split its silicon into 2, backed by real customers and real numbers, that is worth paying attention to.